So continuing with the accuracy and precision, accuracy is how close a measurement is to the known accepted value. Precision is the smallest change in value that can be measured by an instrument or an operator, and it's determined by the size of the random error in the measurements. So, it can be defined in either of those ways. So let's have a look at these targets. Quite often it's taught in the way with using targets. So the little black dots here are the darts where they've hit the dartboard, and being closer to the center represents that you're taking a measurement that is close to the true value of that measurement of that object. So for example, the true length, the true width of the object. So these ones here are quite far away from the true value, from the center of the target, so they're not accurate at all. But because they're repeatedly in the same area, then we can say that they're precise, because there's not much change in the value that can be measured, and there's not much random error. So there's not much that's affecting the measurement that's being taken. In the second example, the darts are all very near the bullseye, and they're also very close together. So because they're very close to the true value, they are accurate, and they are also precise because there is a very small range in the value. There's a low random error, and there's low change in the value that can be measured. And in the third value, they're generally fairly accurate. They're more accurate than in the first example. One there is very accurate, but generally speaking, the average accuracy is quite good. This one, although this one's quite far away. So we're looking for a yes here answer. And then precise, no, they're not precise because there's a large random error. Basically, it's the person who's taking this set of measurements doesn't really know what they're doing, and they're just kind of getting random measurements all over the place. It just so happens that the average is actually relatively close to the true value. Precision problems then. A group of students worked in separate teams to measure the length of an object. Here is their data. The average mean, so we have to add up all of these, okay, and then divide by the number of data, which is 7. So this is the sum of the lengths that's measured. This symbol here is Greek symbol capital sigma. Sum of the lengths being measured is 18.9 centimeters. Divide that through by 7 and you get 2.7 centimeters. Calculate the range by subtracting the highest value from the lowest value. So the highest value being 2.8 centimeters, the lowest being 2.6. So it gives 0.2. Strictly speaking, we should put another 0 on here to represent the same number of significant figures as given in the question, representing 1/100 of a centimeter or 1/10 of a millimeter. Divide the range by 2, get 0.1. This is the approximate range from the average. The error or uncertainty in the measurement can be given by average plus or minus the range. So the average has been calculated, and then you plus or minus the range, and that's the precision of the measurement. And that's how it can be quoted. Now, generally, the error is only given to one significant figure, and the data, or it's either given to one significant figure or it's given to the same precision, the same number of decimal places as the data itself. And the average is generally given to one less significant figure as the whole data set. A second group of students obtained the following data. So again, we've got another set of data, and another 7 teams. They've measured the average length to be the same. precision, where do we get this plus or minus? We do it the range divided by 2. Which group was more precise, or was the precision the same? Well, the uncertainty is the same, so the precision is the same in this case.